So now that I didn't hit record, but the idea is find u to make it simpler, but really recognize it as u and the derivative of u so that you can reverse it using the chain. So we did a bunch of examples, but maybe, well, here's one that's slightly different. The integral of sine squared times cosine. And you realize that, yeah, sine and cosine are like derivatives of each other, at least maybe a minus sign is in there. But you could, one of these could be u and the other could be the derivative, or vice versa. And so you just try lots of things, and then maybe you realize, well, let's see, if I let u be sine, then that's like my function with u in it. The rest of it better be the derivative of that. And that's exactly what we have here. Du is cosine dx. So it lines up perfectly that the first part is u squared, and the second part, that part's there, this part is here. In which case, I've made it a lot easier by substituting that in, and now I can actually do the antiderivative.
I'm actually getting curious about earlier comments saying that substitution was an integral form of chain rule, because I thought that was kind of like a section in chapter 5 where I was just talking about that specifically.
Did that come up in chapter 5?
Kind of. It was a section in which case where there were two upper bounds and lower bounds of an integral. One was a function, one was just a constant, and then you just.
Yeah, that's true. We used the chain rule to compute that related, but this really is. Well, let me write this down, and then we'll just reconfirm or repeat what I was saying.
Okay.
That I can do the antiderivative of u squared to get 1/3 u cubed, and then I can replace to get back to the x's that this would be 1/3 sine cubed. I'm just plugging the u back in. So you can see that if you did try to verify that, well, in order to verify the answer, I take the prime or the derivative of my answer. And in order to do this, you have to do the chain rule because you've got a cube function, but inside of the cube function, you have a sign. Whenever you have one function inside of another, or what's called composition, you have to use the chain rule. And it's 1/3. You do the regular derivative of the cube, so 3 and then squared, but then the chain part here is I have to multiply by the derivative of the inside. So that's sine prime. And the 3's cancel, and I get sine squared cosine, which is right back to where I started. So it really is the reverse of the chain rule in that sense. And, okay. Hang on just a second.
Wait, where did the cosine x for that final equation come from exactly?
Well, what's the chain rule say to do? It says do the derivative of the main function, which is like the cube. So that's 3 sine squared. And then the chain says you multiply by the derivative of the inside.
Okay, because I just got the 1/3 sine to the power 3 over sine to the power 3, and then from there that was the answer because there's something else you can replace.
I'm just saying that is here's the answer.
Okay. Oh, you're just verifying it. Okay.
This is the verification.
Okay.
We haven't done too much of that, and we should, but I'm doing it here. So.
Okay.
Yeah. Okay. You can do this with. Let's try. You can do this with bounds, where you can do the antiderivative. Well, it's not antiderivative anymore. It's a definite integral. So we know that this represents an area. So if we actually drew this function, turns out that there's an asymptote at 5, and between 6 and 9, we can just plot some points. It'll look sort of roughly like this. And so we want to know the area under the curve y equals 1 over x minus 5 from 6 to 9. So when you see this, I still hope in your brain you think, oh, there's bounds, therefore it's an area. Now, how does this work into substitution? Well, this is a basic substitution, that, just for emphasis, I want to let u equal x minus 5. And the reason why is because, well, then it would look like 1 over u, which I know that one. That's natural log. Du is the derivative of this thing. So if I did the derivative u prime, I would get 1, and then I multiply it by dx, so I just get 1 times dx, which is dx. So du and dx are the same. But here's the point, is these bounds, the 6 and the 9, correspond to x. So the 6 and the 9 correspond to x. So if I wanted to change them here, then I would have to convert x's into u's. And the main formula is right there, u equals x minus 5. So that says that u would have to be 6 minus 5 for the lower bound, and would have to be 9 minus 5 for the upper bound. So this would be 1, and this would be 4. And so if I wanted to replace it, I couldn't write 6 and 9 because those are x numbers. I'd have to write 1 and 4. And if you've seen this before, yeah, I know we're going to replace everything, but this really drives home that this is an area. Draw this area and see how it compares to the old area. So if I draw instead of x and y, it's now u and y.
So 6 will be the upper bound in this case?
Just hang on just one second. So if I replace all this stuff and I draw this function, well, it looks like the reciprocal function. If I put in 1 and 4 on this picture and look at the old area, it's exactly the same. It's exactly the same area because I'm supposed to get the same number. So hopefully you can still see this. Didn't pretty well, but let me know if I do. So if I calculate this area, it's exactly the same as calculating the original area because they represent the same thing. And so if you convert these bounds here from 6 and 9 to 1 and 4 just by subtracting 5, that's how you convert these two. Then when you actually do this integral, here, I know that the answer is the natural log of u, technically with bounds on it. And then I can just plug in u equals 1 and u equals 4 and subtract. So I'll get the natural log of 4 minus the natural log of 1, and that's my answer. And technically this is 0, and I get natural log 4 only. But that's the answer to the original problem. If I convert here, I don't have to replace and go back because I've already done all of the replacement here. So that's a shortcut. Let me try one more, and then maybe if there's a question, we can maybe do this one in two different ways. So integral from 0 to 1 of 2x, x 1 minus x squared to the 4th, something like this. So it's an area because I have bounds. I don't know what this one looks like. So I could plot some points and connect it, maybe use a graph, some kind, Wolfram alpha, not on the test, but for this. So it is an area. It does represent an area. If I did try to do a substitution, then I'm looking for things where the derivative is also in there, or at least up to some multiple that I can deal with. So in this case, if I let u equal x squared, 1 minus x squared, then at least this part is u to the 4th. So that part converts over. Unfortunately, I also have to do du, which is, so that's minus 2x dx. But that's good because I've got 2x and I have dx. And I've got 2x and I've got dx. The only thing is I don't have this minus sign in here. So if I moved it to the other side, minus du, that would be 2x dx. So this 2x dx together can be converted into minus du, and minus signs can sort of be put wherever I want. Maybe I'll put it there for this one. But then, just to practice, if I change these numbers, these are x numbers, what do I get when I change them to u numbers? So u equals 0, and u, or sorry, let's just throw off what I was trying to say. The bounds are x equals 0 and x equals 1. So if I convert those using this formula, u would be 1 minus 0 squared for the first one, and it would be 1 minus 1 squared for the second. So it would be 1 and 0. So it looks like the bounds are just reversed on that. So if you did the full substitution, you would get down to this. And that also is an area. So I'm going to do one little trick here. I know that I don't like these bounds where one is bigger than, the lower one's bigger. So let's see if you remember when we reverse the bounds, what it does is it changes from minus to plus or plus to minus back the other direction. Now I can draw this one for u and y. If I did y equals u to the 4th, then that looks, it's like a really steeper than a parabola, and I get that area under there. So whatever the area was before, if I was to draw it, it would give me the same answer as the area there, and that's a pretty easy one. It's just 1/5 u to the 5th, and then plug in my u bound, and I'll get 1/5. So that's one way to do it. That's like method 1. If you've seen this before, you're like, nah, I'm not going to do that. I'm going to do method 2, which is the replacement. And then I don't have to worry about changing these bounds. I can just use the original bounds at the beginning. So here's what I mean by that, is take your function, you do the same u substitution, du is 1 minus x squared, du is minus 2x dx. You convert it, you'll still get minus u to the 5th or 4th, jumping a bit, du. Leave the bounds off just for a second, so that when I do this, I get minus 1/5 u to the 5th. Technically, there's a plus c, but I know for the definite interval, I don't need that. And now do the replace, but a full replace, meaning minus 1/5, I replace the u, and then I replace the original bounds. That's the original. So that when I substitute in the numbers, I'll get minus 1/5, and then I plug in 1. If I plug in 1, I'll have 1 minus 1 squared to the 5th, and that'll be 0. Minus, now plug in 0. So write the whole thing out. Minus 1/5, 1 minus 0 squared to the 5th. And that'll end up being 0 on the front end because it's 1 minus 1. This is 1 to the 5th. So 1 times negative a 5th times a negative, I'll get plus 1/5. And I also get the answer 1/5 like I expected, because it's all supposed to be this area. And so whether it's you replace the u's to give new bounds, or you do all the work, replace the x's back in and use the old bounds, you'll get exactly the same answer. Okay, maybe go ahead.
So what exactly is different from method 2 to method 1?
Well, method 1, I never replace the x's back in at the end.
Okay, so my other question about it was why exactly does for method 1, I kind of understand it because I've done it too, but why is it you can just add a negative to du and replace it because it's not negative in the original equation?
Well, let's look at this, maybe going back to the direction. If I took negative du, so this negative can go here, can go here, can go here. If I did negative du, what I would get is I would get 2x dx, which is exactly this. In class, sometimes you would do this, right? You do dx equals 1 over negative 2x du. Solve it out. Now when I plug this in here, I'll have 2x. I'll have 2x on the bottom. They'll cancel, but now I have this minus sign in there. So it's just a regular substitution that I end up picking up a minus because of this derivative. And if it's a definite integral to begin with, you have two methods you can do it. You can either change the bounds to get a new area, because you'll have the u bounds, or you can replace everything back at the end, and it doesn't matter. You'll end up getting the same answer. So let's try one more here. So 2 to 6, and then we'll jump to the next section. And this is kind of a tricky one. So it's an area. I could draw it. I'm not going to, but it's some area. And so I want to figure out, the problem is I have an X on the inside and I've got an X on the outside. So this one is like, that looks weird. But let's see what happens. So I'm going to rewrite this as X minus 2 to the 1 half. So whenever you're doing integrals, it's kind of nicer to have these powers anyway. So if you told me it's a U substitution, I got to try something. So let's try X minus 2. I know it can't just be X. I've already shown that. If you just did X, everything turns into U's and I have exactly the same problem. It did not get easier. So if I try this, then let's see, what do I got? I at least have U to the half. That takes care of that part. That's why I did this. But I also have dx and I've got x. So how do I deal with that? Well, du, so I take the derivative of this. Although in this case, the derivative is 1. So du is just exactly dx. I'm like, okay, well, that takes care of this one. Dx and du are the same, so put that in. But what about that x right there? And this is where it's a little sneakiness that if I take this equation over here, look at it. U equals x minus 2. So if I solve for x, I get x is equal to u plus 2. So I can take that and plug that in for that first x right there. And so I'll get u plus 2. And now I have converted all of the x's in terms of u, and I get this new one. Now you're like, wait, is that any easier than the original? And in this case, it's strange that it is. So if I distribute this out, u times this and 2 times this, I'll get u to the 3 halves. So I can multiply this out with this, and I'll get 2u to the 1 half. So the fact that I did this little sneaky one is then I got rid of all this square root where I can't distribute it into one that I can. So this one is one that definitely takes some pattern recognition to get used to. But at least now I can just compute these antiderivatives. How do you do that? You add 1 to the power, so that's 5 halves. So 3 halves goes to 5 halves. And divide by 5 halves. And then the second one, the u goes to 3 halves, and I divide by 3 halves. And I don't have to put the plus c because I know in the end I'm going to get a number out of this. But let's go back and we'll do replace. Full replace, I guess. So wherever I have u, I'm going to stick back in x minus 2. So I'll have x minus 2 raised to the 5 halves power over 5, sorry, x minus 2 to the 5 halves. Put that u back in. Then I'm going to put the u back in for the second term, which is the 3 halves. And I'll get plus 2 x minus 2 to the 3 halves over 3 halves. And then I have to do my usual fundamental theorem where I have to evaluate that from 2 systems. So this is definitely a tricky one where not only you have to do a substitution and figure out the pieces, but then the third piece you have to figure out by going back and doing a little bit more. But just to complete this off, let's see what happens. When I stick in 6, I will get 4 to the 5 halves over 5 halves. If I stick it into the second one, I'll have 2 times 4 to the 3 halves over 3 halves. That's the first one. When I plug in 6. When I plug in 2, I'll have x minus 2. So the 2's cancel on both of them. So minus 0 for both of them. So when I plug in 2, I just get 0. So technically, this is the answer. I guess if we wanted to clean it up a little bit, we have to do some algebra here. 4 raised to the 5 halves power. And what that means is take the square root, because it's a half power, and then take that and raise it to the 5th. So square root is 2, so 2, 4, 8, 16, 32. And then when you flip 5 halves to the top, it'll be 2/5. So it's 2/5 times 32. And maybe that's too much in our heads, but that's 64/5 right there. And this one, 4 to the 3 halves. 3 halves means take the square root, which is 2, raise it to the 3rd power, which is 8, multiply that by 2 is 16, then flip the 3 halves to be 2/3. That's 16 times 2 over 3. So plus 32 over 3. Not too terrible, but whatever the area is under this curve, that's it right there. So it can get a little complicated along the way. So we are going to jump ahead to the next section, but maybe let's see. Do you guys have questions on 6.1 homework at this point? Maybe we could just handle those right now.
I didn't understand number 83.
Okay. Okay. So here we go. So minus 2 to 1 of x plus 1 e to the x squared plus 2x plus 1. It looks ugly. It does represent an area of some kind because it's a definite integral. I don't know what that looks like. So what we're going to do is try a u substitution because it's in that section. So I think, whenever you choose u, you want to make sure that the derivative of u is also in there, which means if you're doing polynomials, you almost always want to pick it to be the larger degree one. So this is a square, and this is not. So let's try this one. Du is the derivative. You always go u prime, and then you multiply by dx. So take the derivative of that. It's 2x plus 2, and that's it. Okay. So we tried to plug all this stuff in. I'm not going to worry about the balance for a second. This would at least be e to the u. And now here's if you want, you can do this, and if it works out, everything's great. Dx will be 1 over x, 2x plus 2 du, and let's just sub that in. So I'll get x plus 1 still in there, which is like, I don't want that. But let's hope it balances out by what I'm plugging in here. 1 over 2x plus 2 du. So if everything cancels, then I'm in good shape. If it doesn't, that means I did something wrong. So can I cancel out this x plus 1? The answer is you can, because look at what's in the denominator. You can factor out 2. Think about it as 2 times x plus 1. And now the x plus 1 can cancel. So what's left in there? I've got e to the u, x, du, x. I also have this multiple of a half, which I think it's a good idea to get used to the fact that it's better just to sort of put it on the outside so it doesn't clutter up your brain when you're trying to compute this antiderivative. So that's the full substitution. There's u, there's du, do the algebra, and boom, you get that here. And yeah, that one's easy to do. The first one's hard, this one's easy. So integral of e to the u is just e to the u. And technically plus c, then I'm not going to need it for a definite.
Thank you, sir.
Just to finish it off, do a full replace. I can do 1/2 e to the, plug the u back in, x squared plus 2x plus 1, then evaluate that between the two bounds. So what happens when I stick in -1? I get e to the, well, that'll be 1 because I'll square it, -2 plus 1, that'll be e to the 0. And then minus what happens when I stick in -2, this will be 4, this will be -4, so 4 minus 4, and then so just 1. So I'll end up getting that 1/2 minus 1/2 e to the 1. That'll be, and that number is negative. So if you were to plot this, that means that more area is below the axis than is above. Maybe all of it. In fact, I think in this case, all of it is. All right, other questions?
What about number 85, sir?
Ah, yes. 85. Yeah, this one's not easy. There's a little sneakiness in this one. But if we tried this, suppose we just try this, just try, like we did in the others, just u is x squared minus 6x plus 10. And so that's there, that looks good. The problem is if I did du, it's the derivative 2x minus 6 dx. And now that term right there is nowhere to be found. Not in any multiple of it, it's not going to be able to cancel out. So this is not in the original. So I can't balance it. Can't cancel it. So all that means is that that is not the correct method. So you got to try something else. You got to look through the integral tables to say, well, if I do this, usually I do a derivative or do a substitution and I get to something that looks like something that's in the table. And you look through the table and you start seeing things that look like this. 1 over x plus 1. Ooh, okay. That's not quite the same, but at least it's the only thing in the table that looks like what I'm supposed to do. So in the table, this turns out to be arctan of x plus c. So maybe, I don't know exactly how I'm supposed to get that to look like that. I can't just take away this. But maybe I can do this somehow. And so maybe, I hate to say that math is a bunch of tricks, but in this case, it's sort of an algebra trick. And if I do this, 6x plus 10, I can write it as 6x minus, or x squared minus 6x plus 9 plus 1. You're like, what? Why would you do that? Well, I want to do that because the plus 1 matches up with that plus 1. And the fact that this right here is what's called, it's called completing the square. If you remember that from back in the algebra days. Or
Yes, sir.
So this becomes the integral of 1 over x minus 3 squared plus 1 dx. So I rewrote that using complete the square. Now that looks super close to this. I've got the 1, I've got the plus 1, and I have something squared. It's not quite x squared, but maybe then that can tell us, okay, I need to change it into something squared by doing that substitution. So if I did u equals x minus 3, du will be dx, because the derivative is just 1. And so this will become the integral of 1 over u squared plus 1. So with that one little sneaky trick, you can get down to this. And now this is arctan of u. And I don't need the plus c because I know I'm going to plug in some bounds. So replace and I get arctan of all that mess, x squared minus 6x plus 10. And then I have to sub in 2, 2, and 4. And if I do substitute that in, I end up getting the arctan of something minus the arctan of something else. See if we can work out what those are. If I stick in 4, that'll be 16. I've got a plus 10, 26. I'd subtract 24, so that ends up being 2. And if I plug in 2, I'll have 4 plus 10, that's 14, but I'll be subtracting 12, so that's also 2. So if I did everything right, well, that looks like the answer is 0. Is that right?
Yes, sir.
Okay. So that must mean that when I drew this function up here, that whatever was above the axis is balanced exactly with what was below the axis. And so I'll have to think back what that actual picture looks like. Maybe we can just plot a couple of points here. If I plug in 2, I'll get 1/2. If I plug in 4, maybe I'm trying to think of what's going on here. Does this thing go negative? Maybe it's arctan. Let me draw that. I'll come back to that one because I don't have that in my head. But if I did all the math correct, and double check. Occasionally Hartman gets the answers in the back correct. I want to make sure I didn't put it's easy to miss a minus sign somewhere. Yeah, so it says the answer is pi over 2. So I think I made one little error somewhere. I don't see where it is right off the bat. 4. Either that or maybe either the answer's in the back is not. I think the answer in the
Maybe
back.
not the x minus 3 squared.
Pardon me?
Maybe the x minus 3 squared, like if the factor is wrong.
No, I think the answer in the back is probably not correct. Let me double check with him and we'll see. I mean, every method I did is correct. I don't know. I mean, we might as well. Let's just try it. We haven't done this enough, so go to Wolfram Alpha here. Slow. Integral of 1 over x squared minus 6x plus 10. And from x equals 2 to x equals 4. Oh, yeah, what do you know? What did I do wrong there?
Excuse me, sir.
Never mind. I got it. Just a moment. Yeah, this is silly. What was the U I actually did? It was not this whole thing. That was my error. So this is not right, and this is not right. Try again. What is my actual U that I'm supposed to replace? It's not the whole thing. It's right here.
And the x minus 3.
Yeah, maybe that's what you were saying, and I just wasn't listening. But I'm not a good listener sometimes, apparently. So you will get arctan of 4 minus 3, and that's 1. And then I'll get the arctan when I plug in 2 of minus 1. Okay, I feel better. So this does end up being pi over 4 when you plug it in your calculator, if you just remember that. Minus a minus pi over 4, and that'll be pi over 2. Good. Yeah, so when I was trying to draw that picture, I'm like, nothing is negative, it just looks like that. And so, all right. So minus 3 points for me on the homework. All right. And we'll do one more before we do a break. If you have one. It's usually where Kyle jumps in. You got homework questions, Kyle?
I didn't have a whole lot of trouble with the homework. I'm good for now.
Okay. All right. Well, let's just, we'll do a break, come back, talk about 6.2. Again, chapter 6 is just a ton of these things, you know, in general, where it's, you're doing the integral, and the question is, what is capital F? And it's just hard. It's just difficult to do. We've done substitution, and already it's like, it's easy to make little mistakes, and there's all sorts of algebra tricks you need to do. So we're just trying to figure it out. We got U subs so far, and then just as a hint, I'll write these letters out if you've seen it before. It's called integration by parts. That's what's coming up next. So we'll do a break, come back at 10:30, start talking about that stuff. So see you in about 5 or 6 minutes. No, 5 minutes. So see you then.